In this video, we're going to be going over ionic equations, and this really is going to tie into ionic compounds and what we did back in those lessons. In order to do an ionic equation, we need to be able to read or memorize the solubility chart to be able to figure out what goes into solution and what does not. And so we will be dealing with both aqueous and solids in these equations. For our class, we should be looking for 3 different compounds being aqueous and 1 being left as a solid. Please make sure that you go through every single compound that's given to you, as we're all human and make mistakes, and you want to make sure you get the right one as a solid. Or in the case that the teacher might make a mistake, you want to make sure that there's not more than 1 solid in your equation. So let me go ahead and show you the solubility chart that we will be using in this class. Here is the solubility chart that I will be using. There's a few different types that are out there, but for the most part, with my experience both in high school and college, I think it's best to have a table that you can easily memorize and group things together. However, if you want to use a different solubility chart that you have found, that would be fine. Just know that this is the one that will be given to you, as I do not expect you to memorize this. There's a few things that we need to know to be able to approach this solubility table. The first of which is that we need to look at the left-hand side of the table first to figure out if something is going to be initially soluble or insoluble. So that would be over here. On the left-hand side, you'll be looking for mostly the anions that you're looking at, but you can see at the very top, underneath soluble compounds, that you have some positive charges as well. If that ends up confusing you, I suggest looking at only the anion. That can be helpful. One thing that is wrong on this chart before we move any further is that the sulfate ion, the SO4, right here, is really a 2- charge, not a minus charge, and you'll be able to correct that on your paper and use it that way. What we also need to realize at this point is that soluble means that we are aqueous, and insoluble means that we are solid. So I'm going to write down AQ for aqueous and S for insoluble. Or should I say S for solid, which relates to insoluble. Once you find your anion on this side of the chart, you will want to look for exceptions. And so I'm going to draw an arrow between the 2 sides to kind of show you where your eyes should follow after you find out where your anion is. So for instance, if you have this SO4 sulfate ion, and you figure out that it's soluble, you still want to go ahead and go over to the right-hand side and check that the exception does or does not apply. For this first part at the very top, you have 4 different bullet points here and only 2 bullet points over here. What you need to know is that you only have halides as exceptions and sulfates as exceptions. So if you have a sulfate or a halide on the left-hand side, you need to check the exceptions. If you do not have one of these 2, you do not need to go over to the exceptions. When you go over to the exceptions, if you answer yes for any of these types of elements that are listed, you then become solid or insoluble. The same thing goes for all your insoluble compounds. So if you start out with this bottom left-hand part, what you do need to note is that there are 2 bullet points here, and there are 2 bullet points on the right-hand side. The bullet points correspond to each other. So this first group here that's underneath the first bullet point, you need to read the first bullet point for the exception if you have any of those. For the second hydroxide ion, you have hydroxide exceptions, and so you will always have to read this exception box if you are in the insoluble compounds. So let's go ahead, I'll give you an example problem. We'll work through figuring out what ones are solid and aqueous, and then we'll look into how you go about doing and finding a net ionic equation. Before I forget, if you answer yes to an exception down here, we are no longer a solid, and therefore will become aqueous. On your screen now you can see the example problem that I'm giving you. I will go ahead and give you a full double replacement reaction so that you can start working from the get-go. So for the 4 compounds that are listed, we need to look at our solubility chart and figure out aqueous or solid or soluble and insoluble here before we are able to move on. So let me go ahead and show you the solubility chart at the same time, and feel free, if you do not have a copy of this, to go ahead and take a screenshot of it. Okay, so this is the same one that we were working from and have all the notations on. And so what we want to do is look at our compounds and compare them to our solubility chart. So the first thing I'm going to notice is my anions. I think it's easier to focus on those. And what we have here is chloride and our hydroxide. And so let's go ahead and do the chlorides first. Chlorides are going to fall under a halide. So anything in group 17 is considered a halide. So you can kind of add that to your bank of knowledge there if not already. And so initially we are aqueous here, but we do have exceptions for halides, and that's going to be silver, mercury, and lead. And iron is not one of those. So we're looking right here for this compound here. Chloride, and then iron is not one of the exceptions. So this would make it an aqueous compound. At the same time, we can go ahead and look at our other chloride compound, which is on our product side, as potassium chloride right here. And again, we still have none of these exceptions. So if our answer to this box is no, we don't have an exception, we are still over here in this box. So we have aqueous. So let's go ahead and look at our hydroxides. You'll get used to where things are, but for right now, I might be a little bit quicker than you're finding. So the more you use this, the quicker you're going to be. So hydroxide is here at the bottom. Okay, so you'll have to find that first. And so at first, both of these we want to say are soluble, or excuse me, are insoluble. 1, 2, 3. Now looking for hydroxide, which is right here. Okay, let's just start over. 1, 2, 3. Now that you are done looking at your chloride compounds, let's go ahead and look at our hydroxide. And hydroxide is here right at the bottom, and the more you use the chart, the quicker you're going to be as finding these. And so at first, we know that we are insoluble or solid, but we also know we should only have one solid, and it will not work for KOH and FeOH3 to be insoluble here. So let's look at the exceptions. Hydroxides of group 1 metal cations and barium. So if we look at KOH, K is in group 1 or in column 1. And so since we're saying yes, we do have a group 1 metal, that means that KOH or potassium hydroxide is aqueous. Now by a process of elimination, that means that iron hydroxide should be our solid, but let's go ahead and confirm or deny that assumption. So we have a hydroxide. Going back over here, we do not have a group 1 metal and we do not have barium. So if our answer to this box is no, we want to come back to the first box, which is saying that this is the one that is insoluble or gets the notation of a solid. At this point, we want to go ahead and break apart or dissociate everything that we possibly can. Solids will not dissociate, meaning that they will not dissolve in water, whereas anything that is aqueous will. When we go ahead and break apart our aqueous compounds, we want to make sure that any subscripts become coefficients, and you'll see that in the next line. We want to include all charges, and we also need to make sure anything that is polyatomic stays together as a polyatomic. So before I go ahead and explain the second line here, I do need to point out that I forgot to put this 3 here, which would then make the initial equation balance. So please make sure to update yours with a 3, or at least when you're looking this over, make sure you recognize that there's a 3 there. So what we want to go ahead and do is break everything apart that's aqueous, and so that's what I went ahead and did. My Fe has a 3+ charge because that's what's going to balance the 3 chlorines being negatively charged. I included both my charges. This 3 subscript then becomes a coefficient, which I mentioned before, and I also include the state of matter of aqueous here. My 3KOH now is going to have that 3 distributed to both the K and to the OH. So you can see the 3 is in front of my K and in front of my hydroxide. K is plus, OH is minus, and again, aqueous state of matter. This is going to yield my solid iron hydroxide, and so I just transfer that or copy that straight down. Now that we have this 3 where it's supposed to be, this 3 is also going to distribute to the K and to the chloride, potassium and the chloride, should I say. And so you have 3 K pluses at aqueous state, and we have 3 Cl minuses at aqueous state. This is going to be called our complete ionic equation. And at this point, we want to go ahead and cross out anything that is the same on both sides of the equation. So if you see on the left-hand side and the right-hand side exactly the same thing, we're going to want to go ahead and cross that out. So I'm going to go ahead and get that taken care of and add that this is the complete ionic equation. So now on your screen you can see that I included complete ionic equation is this whole entire line. And then I went ahead and crossed out anything that's the same on both sides. This is similar to any math class, right? And so I have 3 Cl minuses on the left and on the right, and the state of matter is the same. So I can go ahead and cross those out. The same thing goes for my 3 potassium plus ones. So I have 1 on the left and 1 on the right, exactly the same. State of matter, charge, the element, and the coefficient, they're all the same. So I can go ahead and cross them out. The reason why we want to do this is because they are considered spectator ions. They really are not contributing to any of the chemistry. They're just kind of floating around. And so that's why we want to kind of eliminate them from the complete ionic equation. And so now whatever is left over and not crossed out, we want to rewrite, because that is going to be what's left over as our net ionic equation. So let's go ahead and do that. So now underneath the last note of spectator ion, you now see the net ionic equation. If you compare the complete ionic equation to the net ionic equation, you can see the only difference between the two is that the spectator ions are not listed out.